excuse me, this picture depicts a circle in the XY plane. And let's let this point be some point in the XY plane within the circle. Now we want to talk about a sphere of radius A for the hemisphere, the upper hemisphere of the same radius. Okay, so we have this point down here, and from this point we can project up to the sphere, and we get a point on the sphere. Okay, so circle in the XY plane, point within the circle in the XY plane, and a point on the sphere above this point. Okay, this is the key to the understanding the pictures that we're going to draw. Now here we have again the sphere. Here's our point in the XY plane. It's labeled, and we don't worry about the label yet. And here's how high the sphere is. Here's the point where the vertical line above that point intersects the hemisphere. What we want to do is we want to set up an integral that gives us the volume of this hemisphere. Of course, we know what the volume is. We know the volume of a sphere of radius r is 4/3 pi r cubed. So if this is a hemisphere of radius a, the whole sphere would have radius 4/3 pi a cubed, and the upper hemisphere would have half that, 2/3 pi a cubed. And that's what our integral would end up being. Now, there's a point to doing that integral, so we know where that formula comes from, but there's an even bigger point in that we can use that, the same partitioning that we're going to use to set up the integral, to set up an integral for the mass of a sphere if we know its density function, and if we wish, the moment of inertia of that hemisphere about any axis we might wish, although some axes are easier than others. Okay. And you know, of course, when we set up these various integrals, there's no guarantee that we'll be able to actually do the integration. Not all functions are integrable, and if you make the axis weird enough, it might be kind of difficult to, or impossible to do the moment of inertia about that axis. Anyhow, so what we do to describe this sphere, we partition. Okay, what do we partition? Well, we're going to start off by looking at this circle in the XY plane, and we're going to partition the X and Y axes in such a way that we have a description of that circle, and then for any sub-interval, sub-increment within that circle, we'll be able to figure out the corresponding volume by figuring out how high we have to go to get to the sphere. Okay, well, our partition, and this should be familiar, is going to be this. We'll choose to partition with respect to X. It doesn't matter, we could have chosen to partition with respect to Y, but we partition the X interval from -a to a. That would be from here to here. So we partition that X interval, and then for the ith subinterval, Y goes from what to what? Well, in the ith subinterval, the sample point implicitly, and I'm referring back to what we've already done for integrals in 2 dimensions, double integrals, the ith subinterval implicitly has sample point x star, so that by this picture, if this is X and this is Y, once more, just as before, for a typical, okay, we partition from -a to a, we have these subintervals. For a typical subinterval, you have a sample point within that subinterval, and then we have a triangle with one vertex on the x-axis at the sample point, another on the circle directly above, and another at the origin. So we have a right triangle. We know that its radius is a, so the hypotenuse is a. And if we know x sub I star, the sample point for that ith interval, we can easily find how far we have to go to get up, or to get out to the circle, how far we have to go in the y direction, and we conclude that y goes from, no, it's probably hard to read because it isn't real well written. Maybe that made it better, maybe it made it worse. But we go from negative square root of a squared minus xi squared to the square root of a squared minus xi squared. Now this has been done in detail, so we should understand these triangles in this picture. And then we partition that y interval. And we partition it from negative square root of a squared minus xi squared to a square root of a squared minus xi squared, xi star squared. And how many subintervals are there in that partition? Well, we say it's, for each I, we have a partition, we have an interval of the x-axis with a sample point. So for each I, we'll have some number of intervals in the partition. It doesn't have to be the same for every I. So we're going to say we have m sub I subintervals in the ith partition. And we, of course, use the subscript I to indicate that this is a partition of the, corresponding to the ith subinterval of the x. And the intervals, the partition points are numbered from 0 to m sub I. So we have m sub I subintervals. Okay? So we have our partition of the circle. Okay, now all we have to do is figure out how far we have to go above a typical sample point to get to the sphere. And our picture now, I've labeled a point here. You maybe can't see the head of the arrow, but the point right in here inside this little rectangle. That's going to be the sample point of the jth y subinterval within the ith subinterval, and of course the sample point in the ith subinterval of the x is xi star. And I didn't quite say that right. The jth subinterval of the partition of the strip corresponding to the ith x subinterval we'll call j sub I j star. That's the sample point in this rectangle. And of course this is within the region defined by the ith subinterval of the x-axis, the ith subinterval here. Okay, well, by the fact that the distance from the origin to this point on the sphere is a radius, so it has length a, and this was something people didn't immediately pick up on in class, kind of had to drag it out of people. We have a triangle from the origin to the point on the sphere, directly down to the point xi star, yij star in the plane, and then back to the origin. We have a right angle right here clearly because this is vertical and the xy plane is horizontal, so yeah, that should be obvious. So we know that this distance is what? Well, I write it down here, and it's a little hard to see because we've got this triangle, but right here it is, okay? It's just a squared minus the square of this distance. What's this distance? Well, the distance from the origin to xi star yj star is xi star squared plus yij star squared. So when we subtract the square of that distance from the square of the hypotenuse, this is what we get, and this will be our z sub ij. Now, this gives us, well, if we partition z from zero to z sub ij, okay, this point now has coordinates z sub ij equal to this. We can see the partition here. We have z, it might be hard to read, z sub ij 0, that's equal to 0. Z sub ij p sub ij is how many intervals we have in this partition of the z interval from 0 to square root of a squared minus xi star squared minus yij star squared. And Then we have all the subintervals within, and what does this look like? Well, this looks like this here. Now, it looks like this. In other words, we get a rectangular solid. Base is the rectangle down here in the xy plane. The altitude is z sub ij. If this is the ij rectangle of our x and y partition, the height, the altitude is z sub ij. And we partition from 0 to z sub ij, so we get a bunch of small rectangular solids in a stack. And the ijk increment of that stack is represented here. It's going to have a coordinate between 0 and z sub ij, whatever the number of the stack is. And we're using k as a subscript that tells us which interval of this partition we're talking about here. Okay, so well, that's what we have. Now we're going to see how to put that together.